Section 5.4, the fundamental theorem of calculus. Let's begin with this part 1. If f is continuous on a closed interval ab, then integral from a to x ft dt, that is called capital F of x, is continuous on the same interval and differentiable, and its derivative is f of x. That means that that term, integral a to x ft dt, is an antiderivative of f. Okay, here, let's try to find the derivative of these functions by using the fundamental theorem of calculus part 1. For this one, g prime x is directly now sine and 1 plus x squared. And t is replaced by x. This is a sine f of t, and that is now f of x. Okay, for this one, this is not x cubed. But here, by using fundamental theorem of calculus, if we call this as f of t, then it can be written f of x cubed. If we try to use the same kind of notation. Now x cubed for this problem is considered as the variable. So here the variable x and x, x cubed. If you try to make x derivative, then now h prime x, that is same as, okay, first you can make a derivative with respect to x cubed, so that now f prime x cubed and derivative of x cubed, which is 3x squared. We use the chain rule, right? Okay, that means that here, this is now, that is, if you make a derivative and with respect to x cubed, and then here you have to replace t with x cubed, so that is e to the minus x cubed, now same x 3x squared multiplied. Okay, now we'll go this one. Here, rather than top, and now this lower bound is x, then by using a property of definite integral, it can be written with the negative of the integral 5 to x and same f of t, 3t, sine t, and dt. Now we can use the part 1 fundamental theorem of calculus, y prime equal, now minus there, and this portion is changed into now f of x, so that 3x and sine x. Okay. Now for this one, same way, we combine first to change lower bound and upper bound, and then use technique here explode in part B. Okay. So here that is minus integral 1 to sine x, and that is 1 over square root of 1 minus t squared dt. Now by using the technique we used for b, here y prime equal, okay, minus is there, and then t is replaced by sine x, square root of 1 minus sine squared x, and derivative of sine x, which is cosine x. So here, you can stop here, or that is the same as now minus, and top is cosine x, and bottom is, that is cosine x absolute value. Okay. Now, we may summarize the computation technique here. Okay, if you consider, for example, integral, that one is now, this portion is the same as integral from a to g of x, and plus integral a here, and now h of x. You can write in this way. So if you are making derivative for this portion, then that is the same as now here f of gx and g prime x. For that one, you can get minus f of h of x and times h prime x. Right? Okay, that is the formula, a formula you can use later on for general lower bound and upper bound and derivative. Okay, let's go to part 2 of the fundamental theorem of calculus. If f is continuous over a closed interval a to b, and capital F is any antiderivative of f, and then for constant a and b, so that the lower bound, the upper bound is now constant, and the derivative is same as here, the value of antiderivatives measured, and the difference is evaluated. So that here for any antiderivative, the value at end point minus value at beginning point. And here, because of that one, and now to get definite integral over an interval, first we have to find the antiderivative of f and calculate the number f of b minus f of a. So it is called the sometimes evaluation theorem. Okay. And theorem 5.32, the fundamental theorem of calculus part 2, shows a connection between antiderivative and definite integral. This is reason that when we define antiderivative, and we use the sign, integral sign, and to denote the collection of all derivatives. And because of this connection, we did. Okay. That means that, for example, integral without any lower bound, upper bound, f over dx is now the collection of all antiderivatives. But when you try to evaluate the definite integral, you may use any antiderivative. Okay. Okay, let's try to solve this problem. And for this one, now antiderivative for the function is now x cubed minus, and that is 1 over now 16 x to the 4. Originally there is a 4, and that is 1/4 of x to the 4, and plus c, but you may ignore that one. You can put plus c, it doesn't matter. So that is now for f of x, now that is antiderivative. Here, the solution is the same as now f over b is 4 minus f over 1. So that is same as if it is 4, then 64 and minus 1 over 16 and x to the 4 is 256 and plus c and minus f of 1, that is 1 minus 1 over 16 plus c, right? So if you are putting c, then c appear here one more time with the subtraction, so they'll be cancelled, so that when you are trying to evaluate the integral, you may ignore this portion. Okay. So anyway, by simplifying this quantity, you can get the final answer. You can do it. Now so here when you get practical computation, then you can use this notation for given problem. That integral is same as antiderivative x cubed minus now 1 over 16 x to the 4, okay, with a c, that is antiderivative and evaluation from, okay, sorry about that. Here on the lower bound is 1, upper bound is 4. You can use this bar or now bracket like that. Either way you can put, and here you can evaluate. Okay. Now here the given problem is same as from 1 to 8 and x 1/3 is divided. So that let's try to simplify. So that is now x 1 over 3 plus x to the minus 1 over 3. Okay, dx. So here antiderivative is, okay, plus 1, and so that 4 over 3, and is reciprocal is 3 over 4 to the x to, okay, times x to the 4 over 3. That is antiderivative for this portion, and for that one, and plus 1 is 2 over 3, so that is reciprocal is 3 over 2, and here x to the 2 over 3, right? Okay, that is antiderivative without the c, and we are evaluating from 1 to 8. Okay, so for this term, if it is 8, then there is a 16, so that 12. Okay, rather than that way, okay, let's do a little bit more detail. 3 over 4 and times, when x is 8, then there is 16, x is 1, then 1, so that 16 minus 1 is 15, plus 3 over 2 times, this is 8, then x is 8, and there is 4, minus 1 is 3. So you can simplify this one. Now, for this one, here, okay, you can write this one in this way. Half is coming out, and from 0 to pi over 2, and then now there is 1 plus cosine 2t and dt. Okay. Now, for that one, here, this is half is there, and then that is now x. Okay, we are using t variable, so let's try to use t. Okay, here that is t, and plus antiderivative of cosine is sine, so we are putting here now sine 2t. If you make a derivative for that one, 2 will come out, so that you have to put half here. Okay, and we are evaluating from 0 to pi over 2. Okay. Now, and then here that is half times and pi over 2 minus 0 is just simply pi over 2. And then here, once t is pi over 2, then there's a sine pi, which will be 0, and 0. Once t is 0, then that is 0, so that you can ignore this portion. So that's the answer. Okay. Okay. Now let's try to evaluate the integral. Okay. For part A, the first portion, the antiderivative is natural logarithm of x, absolute value, and plus, now for that portion, okay, e to the minus 3x, exponential function, e to the x is always a derivative will be the same as itself, okay, like that. So antiderivative of that one must be this one, along with if you are making derivative this term, then minus 3 will come out, so that you are putting 1 over minus 3 here. Then this whole thing, after differentiation, will become that. Okay? Now, so that this is antiderivative. Now you are evaluating from here 1, 2, 3. Right? Okay, that is same as for the first one, natural logarithm of 3 minus natural logarithm of 1, which is 0. So that is natural logarithm of 3. Now minus 1/3 is there. And then here, if that is 3, then that is e to the minus 9 minus here x is 1, then e to the minus 3. Okay. Now let's go to this one. Okay, for this one, the shape over there, it looks like a perturbation of 1 over 1 plus x squared. That is, in fact, you can get from arctangent of x. The derivative of arctangent x becomes that. So rather than x, you are using 2x, then that will become 2x whole thing squared, which is 4x squared. So here, for this term, the main body of antiderivative must be arctangent of 2x. Okay, so you have to put here now a coefficient. Now, if you are making derivative for that one, then that is same as now 1 over 1 plus 2x squared, and then derivative of 2x, which is 2. So 2 is appearing, so that if you are putting 1/2 here, then 2 and half, they cancel each other. Okay, so that is antiderivative. Now we are evaluating the capital F of x from 0 to 1 over 2 square root of 3. Okay, that is same as now half. Okay, now arctangent here 2x is same as 1 over square root of 3, and arctangent 0 is 0. Okay, now that is same as in this way. Okay, that is basically okay. We have to find this one, the quantity, the angle, theta. So that portion is theta. And that is square root over 3. That is 1. Then that will be 2. So the angle theta must be pi over 6. So here, 1/2 times pi over 6, which is same as pi over 12. Okay. Okay. Now, we'll see here mean value theorem for definite integral. And this one, okay, f is continuous. That is condition. F must be continuous. If it is not continuous, then you cannot say that. Then, at some point, which means there is point C between A and B, such that this average value, that is defined to be average value of f, and there is a point C such that function value at C is the same as average value of f. It can be proved quite easily, and so that if you are interested in, then try to read the proof. Okay, here we want to find the average value of f of x given as x times 1 minus x over 1 and 3. So here, first we have to get integral from 1 to 3 f of x dx. Okay, that is same as from 1 to 3. Now, x 1 minus x same as x minus x squared dx. So here that is a half x squared minus 1/3 x cubed, and evaluation from 1 to 3. So for the first one, half times, that's 9 minus 1, so it is 8 minus 1/3. That is here 27 minus 1, which is 26. So that is now, first part is 4 minus 26 over 3. So it is minus, there is, which is, that 4 is the same as 12 over 3. 12 minus 26 is minus 14 over 3. So the average value of f is the same as, now the interval length is 2 from 1 to 3, and the integral, which is minus 14 over 3. Right? So that is same as minus 7 over 3. Okay. Show that if f is continuous on interval a to b, and if integral is 0, then f has a 0. It should be. Now, here, let's try to visualize the problem. From a to b, the integral continuous function, and its integral is 0 means that there are two cases. F is completely 0, or if somewhere is positive, then same amount must be negative, so that this area, that area should be cancelled out. So integral must be 0. In any case, completely 0, and we also we can find a 0. And now in this case, some portion is positive or some portion is negative, then it crosses the horizontal line, because f is continuous, always happening. So that is a 0, right? Here, this is a net change theorem, which is almost the same as the fundamental theorem of calculus part 2. Okay. Here, for differential function, f of x, the net change over the interval a to b is integral of its derivative. Here now, derivative f prime integral from a to b is same as now fb minus fa. This is in a sense another form of part 2 fundamental theorem of calculus, and it can be interpreted in this way. If Cx is the cost of producing X units of a certain commodity, then C prime X is the marginal cost. From the net change theorem, okay, we can write in this way: C prime integral from x1 to x2 is same as Cx2 minus Cx1. Now we move the Cx1 to the right side. But this can be interpreted in this way. The final cost, Cx2, is the same as the initial cost, Cx1, plus and net change for the production increase from x1 units to x2 units. Okay, that is part 1 of the section. Will continue in the part 2. Thank you.